Welcome to the Chapter 2, Section 4 video, where we'll be looking into how to find the zeros of polynomial functions. Remember, in our last section, we looked at finding zeros by factoring. This is going to look at finding the zeros if the polynomial doesn't seem factorable, or if it's a higher degree that you aren't sure how to factor. So the first thing we're going to look at is long division and the division algorithm. Then we'll look at the remainder and factor theorems, which are very closely related. We'll look at synthetic division, which is like a shortcut for long division, but it only works in some cases. Then we'll look at the rational zeros theorem, and that's where we'll actually start being able to solve some of these types of questions. And then lastly, we'll look at how do we know that we have all of the zeros. We'll look at upper and lower bounds of the zeros. So that's different than looking at boundedness of a function. And why is this important? These topics help identify and locate the real zeros of polynomial functions, which is really important when we're looking at solving for specific properties of polynomials. So we're going to start with long division for polynomials. So we'll say f of x divided by d of x gives us q of x, that's the quotient, plus if we have a remainder, we'll call it r of x, and it's a remainder, so it still has a denominator. An example of this, if I have 7 divided by 3, we can say 3 goes into 7 2 times with 1 remainder, right? So essentially, we're looking at this division algorithm from a new light. And specifically, we're looking at it for how does this apply to polynomials? Another way of writing this same statement, if you think about taking this and multiplying everything by d of x, we can also say that f of x equals the quotient times the denominator plus the remainder. In our example, what that would be looking at is 7 equals 2 times 3 plus 1. So let's try one. Use long division to find the quotient and remainder when 2x to the fourth plus x cubed minus 3 is divided by x squared plus x plus 1. So if I'm dividing this, I want my numerator, 2x to the fourth plus x cubed minus 3, dividing it by x squared plus x plus 1. One of the most important things to remember when we're doing polynomial division is placeholders. Now, what does that mean? Well, notice if we look at our numerator, it's descending. We have a 4th degree term, we have a 3rd degree term, and then we skip right down to our constant term. So we're actually missing our 2nd degree and 1st degree terms. And so in order to perform our division, we need to have what's called placeholders. We need to put in zeros for those terms. So I'm going to write this as I would write a normal division statement. The numerator goes on the inside, it's in and out, like the hamburgers. So that's 2x to the fourth plus 1x cubed with my placeholders 0x squared plus 0x minus 3. Now, the reason those placeholders are important, just like when we're dividing numbers, we divide by place value. And so those placeholders are going to make our place values line up. In our denominator, we already have all of our places. So we have x squared, x to the first, and no x. So we don't have to put any placeholders for our denominator. Okay. Vocabulary-wise, we can call this the divisor, and this is the dividend. Dividend with a D. Dividend. Okay, so division. Let's just remind ourselves if we have, let's use the example from before, 3 into 7. I would say how many times does 3 go into 7? So 3 goes into 7 2 times, and then we would say 2 times 3 is 6, subtract that from 7, and we get the remainder. So what are our steps? First, we identify what do I need to divide? I need to divide the 3 into the 7. Then we actually divide. How many times does it go in? It goes in twice. Then we multiply. 2 times 3 was 6. And finally, we subtract. So all of those steps that we use for division of numbers, we're going to now apply to division of polynomials. So step 1, identify. I want to say how many times does x squared go into 2x to the 4th? Well, it goes in 2x squared. Another way of asking that is, what do I have to multiply x squared by in order to get 2x to the 4th? So in order to get 2x to the 4th, I multiply 2x squared times x squared. So I identified, we divided, next we multiply. 2x squared times everything, right? We're distributing here. So that's 2x to the 4th plus 2x cubed plus 2x squared. And now we can see why those placeholders from earlier were important, because without that 0x squared, I wouldn't have my like terms lined up. And lastly, we subtract. Now, I like to distribute that subtraction, which means changing all of my signs, right? -1 times everything in here changes all of my signs. So if you distribute your negative, then you're working with addition instead of subtraction, and that tends to lead to fewer calculation errors. So our first terms should always cancel out. Then we have 1 minus 2, which is -1x cubed, and 0 minus 2, which is -2x squared, and then bring down my plus 0x. All right, so next, and I'm going to go ahead and switch colors so that it's easier to follow. So that was kind of our first step of the division. Next, we're going to do all 4 steps again. Identify. My x squared is now going into -x cubed. So what do I have to multiply x squared by? I need to multiply it by -1 times x. So -x times x squared gives me -x cubed. -x times x is -x squared. -x times 1 is -x. And then we subtract. Distributing my negative, now I can add. First term should cancel out. -2 plus 1 is -x squared. 0 plus 1 is plus x. Bring down my -3. Next step, next color. I'm going to switch colors again. So I have x squared goes into -x squared. I can still multiply x squared by something to get -x squared. And this time I'm multiplying by -1. Distribute that out. I have -x squared minus x minus 1. Subtract. Distribute. Cancels. My next term also cancels. -3 plus 1 is -2. Now, because I canceled 2 terms here, if I had more terms to bring down, I would bring down 2 terms, right? I have 3 terms in my divisor, so every time I'm dividing into the first 3 terms. So if I cancel out 2 terms that go to 0 in a row, I would have to bring down 2 terms to keep dividing. But we don't have to, because -2 is our remainder. How do I know that that's our remainder? The degree of -2 is less than the degree of our divisor, right? My denominator has a degree of 2, so the remainder has to have a degree smaller than 2. Okay, I'm going to go ahead and erase our little division example here and write our answer. So what is our final answer? So we want to find the quotient and the remainder. So we can say 2x to the 4th plus x cubed minus 3 divided by x squared plus x plus 1 equals our quotient, which is 2x squared minus x minus 1, plus the remainder always goes over the denominator. So -2 divided by x squared plus x plus 1. Now, plus and negative is the same as subtracting. So you could also write this, if you didn't want to do plus and negative, you can also write this as minus. But I always write it as plus the negative first to make sure that I'm not just taking the leading negative. I have to factor out a negative from the whole numerator. Right? Simplifying fraction rules, I can only simplify it out if the whole numerator is negative. In this case, we only have 1 term, so we don't have to really worry about that. So here is our quotient and remainder. Let's take a look at our next slide here. The remainder theorem. So we were able to find the remainder. We calculated the quotient in order to get the remainder. But if I wanted to just check what the remainder is, there's a shortcut. And that is that if I take a polynomial and I divide it by a linear factor, a linear polynomial, so just x plus or minus a number, no x squared, no x cubed, just x plus or minus a number, then we can find the remainder by finding f of k. So we would say, what makes this 0? And we would do f of that number. So whatever number makes that denominator 0, if we find f of that number, it will give us the remainder. So let's see if we can apply it. Find the remainder when f of x is divided by x plus 3. So we have 2x squared minus x plus 12 divided by x plus 3. Okay, so we can do the long division like we did in the last slide. And as a matter of fact, I will show you that method. But first, let's see if we can use the remainder theorem. And so the remainder theorem says, what would make this 0? X would have to be -3 for that to be 0. So I want to find f of -3. So that's 2 times -3 squared minus -3 plus 12, which gives us 2 times 9 plus 3 plus 12. 2 times 9 is 18, plus 3 and 12 makes 15, gives us 33 should be our remainder. Let's see if we can find that same remainder by using long division. So I say x plus 3, no placeholders needed, divides into 2x squared, that's degree 2, degree 1, degree 0, no placeholders needed. First, identify. X goes into 2x squared how many times? I would have to multiply by 2x. Distribute, that's 2x squared plus 6x, and then subtract. I like to distribute. Those cancel out. -1 minus 6 is -7x. Bring down a plus 12. Identify. X goes into -7x, -7 times. Distribute, -7 times x, -7 times 3. Subtract, I like to distribute. First term cancels out. 12 plus 21 is 33. Can x go into 33? No, 33 has a smaller degree than x to the first, and so that's what tells us that this is our remainder. Notice we got the same answer both ways. That's what the remainder theorem says. Instead of doing division, I can substitute the value that would make my denominator 0 into the numerator, and I will end up with the value of the remainder. Let's take a look at why that's useful. Well, the remainder theorem said that if I have a value, if I have f of x divided by x minus k, f of k is the remainder. Well, in order for something to be a factor, that means it divides in evenly. And if I have something divide in evenly, if the remainder is 0, then it divides evenly. And if it divides evenly, then we call it a factor. Okay, so what that means is if I have f of x divided by x minus k, and I find f of k equals 0, then that means that f of x divided by x minus k equals g of x with no remainder. Another way of saying that is that f of x equals g of x times x minus k. So do you see how we just factored f of x through division? We found that x minus k is a factor of f of x. So if the remainder is 0, then the denominator is a factor of the numerator. It divides in evenly. Let's take a look at why this is so important. So remember, last class we were factoring in order to find the zeros. And now we're saying, well, if we can't find the zeros that way, we can try division. And division is how we got this remainder in factor theorem. So for any polynomial function, we can call it f. And if we're dividing it by x minus k, so again, we're looking at this same fraction of x minus k, where k is just a number, k for constant, okay? So when we divide by a factor of x minus k, x equals k is what we're hoping will be a 0. We're hoping that it will divide in evenly so that it will factor out. So x equals k is a solution or a root or an x-intercept of the equation when f of x equals 0. Okay, k is a 0 of the function f. K is an x-intercept of the graph of y equals f of x. And x minus k is a factor of f of x. All four of those say the same thing. So notice our key terms here: solution, root, 0, x-intercept, and now we're adding to that list factor. Synthetic division is, again, with this very special case of dividing by a linear factor. So x plus or minus a number. We cannot use synthetic division if we have an x squared. We cannot use synthetic division if we have x cubed. Even if it's a binomial, meaning just two terms, it only works if the degree is 1. Degree has to be 1. Okay, so if I wanted to divide this, normally I would say x minus 1 divides into, and then I check for placeholders. I go 3, 2, 1, 0. I don't need placeholders. So I like to check that before I copy it down. Sometimes I forget, and then I'll notice as I'm copying it down, hopefully. But always be thinking about placeholders as you're drawing your division. So that's 3x cubed minus 2x squared plus 1x minus 5. Okay, well, when I'm looking at identifying and dividing, I'm really just looking at those coefficients, right? So synthetic division gives us a way to divide with just the coefficients, and then we don't have to worry about the x's. So let's do the long division first, and then I'll show you the synthetic division, and you'll start seeing that the same numbers are appearing in both methods of division. So long division, identify, divide. So 1 goes into 3 times, x goes into x cubed, x squared times. Multiply, 3x squared times x is 3x cubed minus 3x squared. Subtract, distribute. First term cancels out, should every time. Negative 2 plus 3 is 1, so that's just x squared. Bring down plus x. Again, identify, x goes into x squared, positive x times x is x squared minus x, subtract, distribute, cancel. That brings me to 2x minus 5. Identify, x goes into 2x plus 2. 2 times x is 2x minus 2. Subtract, distribute, minus 3 is the remainder. Okay, so when we do synthetic division, what we're going to do is, again, we're going to say what makes this 0. X minus 1 is 0 when x is 1. So there's my 1. And then I like to put a box around it. There's a couple different ways to show synthetic division. Some people put the box this way, but I like to put my box around the 1, and then I just put a line down here. So you'll see it both ways when you're looking at synthetic division. Now, the reason I like to put the box around my 1 is to remind me that that is the number that I'm testing. That's the number that I'm dividing, okay? Just like when I find f of 1, I'm finding the remainder when x equals 1. And then we're going to take our coefficients, just the coefficients. So 3, negative 2, 1, and negative 5. 3, always looking for placeholders, negative 2, 1, and negative 5. Okay, so here's the process for synthetic division. Just like when we were dividing, our first coefficient is going to be whatever our leading coefficient was, because I'm just dividing by 1. So the 3 is just going to drop down. Always the first number just drops down. And from here, we're going to do 3 times 1. I want to make it look like multiplication. Let's see, 3 times 1. So 3 times 1 is 3. And then we add. -2 plus 3 is 1. Then again, times 1. 1 times 1 is 1. And then we add 1 plus 1 is 2. Times 1. 2 times 1 is 2. -5 plus 2 is -3. This last number also gets a box. And I should really do it in red to show that that's a structure. Whenever you're doing synthetic division, that last number is always the remainder. So I want to show you the parallels here. So that 1 is from this 1 here, but it's the opposite. So x minus 1, then I'm dividing by 1. The 3 here, 3, -2. So the coefficients from my dividend go into my top row of synthetic division. And then we have our quotient down here, 3, 1, invisible 1, 2, -3. And then we have one more set of numbers that we can find, which is this 3 here is actually this 3. The 1 here is actually this 1. The 2 here is actually this 2. So what we're finding, this second row of our synthetic division table is actually the numbers that we got from multiplying our coefficients times our k value. Okay, now the reason I'm showing you where all of these numbers come into play is to show you that synthetic division is exactly the same process as long division, but it should take a little bit less time and a lot less space. And since it's more compact, that means that there should be fewer chances to make mistakes. However, if you don't practice it, then you're going to make more mistakes, right? So synthetic division is going to be a very useful way of dividing, because a lot of times when we're dividing to find a 0, we are dividing by just a single number, x minus some constant. So almost always to find zeros of polynomials, specifically for the process that we're looking at for the rest of this section, we'll be able to use synthetic division. So synthetic division, it takes some time. It's got a steep learning curve. Hopefully you saw it at least a little bit in Algebra 2, but we're going to be using it a lot. And so it's a process that you really want to make sure that you're practicing and understanding the process of, and not just trying to find some hidden patterns. Okay, because a lot of times we're looking for, oh, well, the pattern is 3, 1, 2, 3, right? But that's only specific to this polynomial. That's not specific to synthetic division in general. So I warn you away from trying to just look at the numbers and the patterns and look for the process. I mentioned that using synthetic division, a lot of times we're going to be dividing by just a number. And this is why we can just choose a number to synthetically divide by. So this is our rational zeros theorem. And we're going to have some practice using synthetic division in just a second. So our rational zeros theorem says, suppose we have a polynomial, let's call it f, and the degree is greater than 1. So it's not a linear polynomial. It could be quadratic, it could be cubic, it could be quartic, it could be higher degree. Okay, when we're looking at our polynomial, we always have our coefficients and we always have our constant. Now those coefficients could be 0, except for our leading coefficient, because then we would just exclude that term, right? So we're always going to have a leading coefficient, and we could have 0 as our constant. Okay, so this is called, remember, our leading coefficient. and this is our constant. The constant has no variable. Okay, so with every coefficient where we're looking at our leading coefficient is not 0, and if our constant is not 0, then we can use this tool. If our constant was 0, then we would factor out an x, and then we would have this case, right? So if our constant is 0, that means all of our terms have at least one factor of x. We would factor out the x, and now we have a polynomial that fits this description. So no matter what our polynomial is, we can we can factor it to the point that we have this specific setup for f of x. Then we can say x equals p over q is a rational 0. Notice it's a fraction. So we can get fractions to test where p and q have no common integer factors. So we're going to simplify our fractions. Then p is an integer factor of the constant. So we're looking at that last term. And q is a factor of the leading coefficient a sub n. So what does that mean? Well, it means that the only way to get a rational 0 from a polynomial, a rational value that could be our x-intercept for a polynomial, is from a factor of the constant, a factor of our a sub 0, divided by a factor of our leading coefficient, that's a sub n. So what does this look like? If I have f of x equals 5x squared plus 3x minus 4, then the only possible rational zeros that I have for here are the factors of 4 divided by 5. So factors of 4 include 4 times 1 and 2 times 2, or 1, 2, and 4. The factors of 5 include just 5 and 1. So my entire list is going to be, I'm going to write them out this way, 1 divided by 1, 1 plus or minus, because I could do -1 times -1. We'll do 1 divided by 5, 1/5, still plus or minus. 2 divided by 1, 2 divided by 5, 4 divided by 1, or 4 divided by 5. So it's not just the one fraction, it's all of the factors of the numerator divided by all of the factors of the denominator. So 1 over 1, 1 over 5, 2 over 1, 2 over 5, 4 over 1, 4 over 5. Okay, let's apply it. So putting all of that together, find the real zeros of the polynomial function. Find all the real zeros. Notice that's rational and irrational. So I'm also going to show you how to find irrational zeros. Find all the real zeros of f of x equals 2x to the 5th minus x to the 4th minus 2x cubed minus 14x squared minus 6x plus 36, and identify them as rational or irrational. Well, when we have a problem like this, our very first step is to identify potential rational zeros. And so that's last over first. So we need to find the factors of 36 divided by the factors of 2. Luckily, the factors of 2 are just 1 and 2. But there are quite a few factors of 36. So I'm going to start with 1 times 36. It's even, so that could be 2 times 18. 3 goes in, 3 times 12. 4 goes in, times 9. 5 does not. 6 does. 6 times 6. Once I have numbers that I don't have any more factors between those two numbers, I know I've found my complete list of factors. Because the next factor would be 9, and we already have it here as 9 times 4, right? So once I get to the bottom of that list, where there are no factors between my last two numbers, I know I have a complete list of factors. But then we have to put them all in fraction form. So I need all of these numbers over 1, and then also all of these numbers over 2. So let's start with over 1, my list of possible rational zeros. So we have 1 over 1, which is 1, 2 over 1, all of these over 1. So I'm just going to write them as their whole number. That's 3, 4 over 1, 6 over 1. I have 6 again, but I don't need to write it twice. 9 over 1, 12 over 1, 18 over 1, and 36 over 1. And then we do the whole thing again over 2. So now I have 1 over 2. 2 over 2 is already 1. I already have that on my list. I don't need to list it again. So what we're going to find is all of our even numbers here should already be on our list. 3 over 2, 4 over 2, already on my list. 6 over 2, already on my list. 9 over 2. 12 over 2, already there. 18 over 2, already there. And 36 over 2, already there. So that's actually the end. Okay, now we don't have to test all of these numbers. That would be a lot, right? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are actually 24 numbers here that we could have as potential rational zeros. So how do we narrow this down? Well, the way we're going to narrow this down is by actually looking at the graph. Okay, this is a 5th degree function with a positive coefficient. So I'm expecting it to look something like this, right? But remember, in the middle, it could do a bunch of things. But it's degree 5, so we know it changes directions at most 4 times. Put it into the calculator, so this is what it looks like. What we can do is we can look at the zeros that we already have, and then we can test them from there. I'm not sure where my list of zeros went, but I'm just gonna go ahead and looking at our graph, let's pick which ones we should test. Okay, well, look at the scaling of this, right? And hopefully you did this on your calculator. If not, go ahead and try typing this into your calculator. Let me put the function back on screen here. All right, there's the function back. So how do I know what numbers to test? Well, this is going from -6 to 6. So that makes this -2, and this is +2. So I definitely want to test 2, right? Because it looks like the graph goes through 2, and it's on our list. Okay, I also want to test what this number could be from our list. So remember the fractions from our list, hopefully you have it written down in front of you. The fractions from our list were 1/2, 3/2, and 9/2, right? And all of those are plus or minus. ... Okay, so what fraction could that be? Well, 1/2 would be closer to between 0 and 1. This looks like it's between 1 and 2. Okay, so I'm going to guess 3/2, plus or minus 3/2. That's what those look like. Okay, now if it's not one of those values, then that means it's not rational. That means it's an irrational zero. Okay, so what do I want to start with? Well, let's start with the one that's not a fraction. Let's start with 2. So how do we test it? Well, I want to test if 2 is a zero of this function. Well, if it's a 0, that means it has a remainder of 0. So we want to test 2, or test an x value of 2. So I want to find f of 2. Or I want to synthetically divide by 2. I'd like us to practice synthetic division. So let's practice with our f of x. So if I'm synthetically dividing by 2, I'm going to check decreasing order 5, 4, 3, 2, 1, 0. I checked all of my degrees are there. I don't need any placeholders. So starting with degree 5, my coefficients are 2, -1, -2, -14, -6, and +36. And then I put a line, and I'm going to put my remainder box. And here come the calculations. So our first number always just drops down. Next, we multiply by 2. So we get 4. And then we add. 4 plus -1 is 3, times 2 is 6. 6 minus 2 is 4. Times 2 is 8. 8 minus 14 is -6. Times 2 is -12. -12 plus -6 is -18. Times 2 is -36. Plus 36 is 0. That makes us happy. Because what that means is that x minus 2 is a factor of f of x. And not only that, but it actually gave us the quotient. That bottom line, remember, was our quotient. So how do we rewrite that as the quotient? Well, we divided by a first degree polynomial. So this was x to the 5th. This becomes x to the 4th. So this is equivalent of 2x to the fourth plus 3x squared plus 4x, 4, 3x squared, 4, 3, 2, 1 minus 6x minus 18. Come on, pen. Okay, so all we did is we decreased the exponent by 1. I had x to the fifth, decreases to x to the fourth, and then it decreases by 1 for each term. If it's positive, it stays positive. If it's negative, it stays negative. Okay? But I'd like to test other zeros. And so I'm not going to rewrite it as its function yet. I'm going to leave space underneath my synthetic division because what I'd like to do is divide my new polynomial by my next factor. Because we just factored, right? We wrote f of x equals the quotient times my divisor. So I can say okay, I'm going to erase this, but I'm going to write down what we know from this division. So we had f of x, and we divided it by x minus 2, and we got a quotient with no remainder. So that means that I can multiply both sides by x minus 2, and I really found a factored form of f of x. So I can say that f of x equals x minus 2 times this quotient right here. Okay, if I want to factor f of x, really what I want to do now is factor the quotient. And so instead of going back and dividing f of x again, in order to test my next zero, in order to test my next x-intercept, I'm actually going to test it in my new quotient. That's the new formula, the new polynomial rather, that I would like to factor. So now we need to pick the next number to test. So we can pick 3/2 or -3/2. Doesn't matter which one. I usually go for the one that's going to be a little bit easier, so I'll go for the one that doesn't have negatives. That's just my preference. So I'm going to test x equals 3/2. So what I'm going to do, I have my 3/2, and I'm just going to copy the coefficients from above. 2, 3, 4, -6, -18. And the reason I'm dividing by the quotient is because I'm continuing to factor. So I'm not going to go all the way back to f of x and factor it, although I can do that. But I have a smaller number to use, so I'm going to make it easier on myself. So here we go. Synthetic division. Drop the 2, multiply by 3/2. Now, a trick is when you're using fractions, your synthetic division should clear out the fractions. You shouldn't end up with these hideous fractions because that tells me you're going in the wrong direction. Your parts are getting smaller and smaller and not necessarily closer and closer to 0. So if you end up with some kind of really unmanageable fractions, that's a hint that it's probably not going to work. So times 3/2 gives us 3. 3 plus 3 is 6. Times 3/2. If I reduce, 6 over 2 is 3. 3 times 3 is 9. 9 plus 4 is 13. Well, 13 is not even. So when I multiply by 3/2, it's going to turn into a fraction. There's no way to simplify that fraction. So I'm going to pause right here and say, well, instead of testing 3/2, remember how I said we could also have tested -3/2. I'm going to say, well, what if I change it to the -3/2? Does the same thing happen? Do I end up with these fractions? So I'm not going to erase that. Instead, I'm going to say, what if I divided by -3/2 instead? So I'm going to do -3/2 over here with the same coefficients, 2, 3, 4, -6, -18. And I'm going to test it. Here, 2. 2 times -3/2 is -3, gives me a 0. 0 times anything is 0, gives me a 4. So far, these are not giving me fractions, right? 4 times negative 3 halves. So 4 divided by 2 is 2 times negative 3 is negative 6. So that's negative 12. Negative 12 divided by 2 is negative 6. Negative 12 divided by 2, negative 6. Negative 6 times 3 is 18. Plus negative 18 is 0. So that worked out, right? And the reason I switched halfway through doing the synthetic division is because I was about to get a fraction within my synthetic division. And if you're getting fractions within your synthetic division, it's probably not right. It doesn't mean it will never happen, but it very rarely happens. Okay, so if you start getting fractions in your synthetic division, try a different number. Try something that's going to make it a little bit easier. So we have x minus 2 as a factor. We have x minus 3 halves. So we have x minus 3 halves as a factor. And when we look at this, I say, well, wouldn't it be nice if it wasn't a fraction? So let's multiply it by 2. That's 2x minus 3 as a factor. Now, the reason I can do that is because if we look at our function, notice it has that leading coefficient of 2. That means at least one of our factors has to have an a value. It can't just be x plus or minus numbers. One of them has to have a 2. And so I'm choosing to put that factor of 2 into this factor. So what do we have so far? We have, at the top, I'm going to write f of x equals our first factor, which was x, x minus 2. Our next factor, which is 2x minus 3. And then we have our remainder, our remaining factor, I should say, which is from our second round of synthetic division. So this was an x to the 5th. Our answer here was x to the 4th. So this was x to the 4th. Then our answer here is x cubed. So that's 2x cubed plus 0x squared plus 4x minus 12. Okay, so we're going to take that factored form and see if we can solve just the 2x cubed part, right? Because we tested our 3 rational numbers. 2 of them worked, 1 of them didn't work out. So then that tells me that this last 0 might be irrational. So let's take a look at that as our option. So there's my factored form, okay? And then I want to say, well, can I find the zeros of this cubic function, because those will also be the zeros of f of x. So there's my cubic function. I can put it in my calculator and I can see that this 0, this one right here, is the same value as this one. It's the same value because it's whatever x value makes that 0 is also the x value that makes f of x 0, okay? It wasn't 3 halves, and 3 halves was the only rational number that could have been that point. And that tells me that it is irrational. And so to find that irrational 0, we're going to use the calculator. And in order to do that, we're going to second calc 0. So I'd like you to try it and round your answer to 3 decimal places. Okay, so hopefully what you got, you did second calculate the 0, you put a right bound and a left bound and a guess, just hit enter again. And what you should get is that x is approximately 1.456. This is irrational. So when you're calculating the 0 that way, you'll either get a rational number like 1.5 or 2, which we can also have done for these methods. You can find these other 2 points that way, okay? But that won't give you the factored form of f of x. So you can still use your calculator as a tool, but I want you to know how to do this part by hand as well. For the irrational zeros, for now, we are going to use the calculator just for this lesson, and then down the road, we'll be able to do it by hand. Okay, now looking at this graph, and hopefully you had a chance to play around and zoom out on the graph, we can see that there aren't 2 more x-intercepts. So what happens to the other 2 potential x-intercepts? Well, those 2 other values that would make f of x 0 are complex. They are not real numbers. They have an imaginary component. And so we only have 3 zeros. We have 3 zeros, and that is x equals 2, which is rational. We have x equals 3/2, which is rational. And then we have x equals 1.456, which is irrational. Okay. In this class, we will only ever have at most one irrational zero. And therefore you can find all of the rational ones. And then if there's one more that it doesn't work with any of your rational zeros, it will be the irrational one that for now you can find with your calculator. And later we'll look at how you'll be able to find that by hand. If it's a degree 2, you already know how to find those irrational zeros with the quadratic formula, right? This one is a degree 3, so I don't expect you to know how to do that by hand yet. Okay, but how do we know that we have found them all? So there's one last concept here. This is our last slide that we'll do together, and then there's one practice problem that I'll have you do as homework. So the last thing that I want to talk about is how do I know that I've zoomed out far enough that there aren't any zeros outside of my window, right? Because we said you might have to zoom out as far as positive to negative 36 for your x values. And you can do that by just changing your window on your calculator, right? But what if I don't want to do that? And maybe I have to zoom out to like 100 or something, and then that's just such a huge window. Well, there's an upper and lower bound test for real zeros. And what that tells us is if I put this number into my synthetic division and I look for the answer pattern, it will tell me if there are any zeros out past that. So I'm going to do kind of a number line example here. For upper bounds, the test is only valid for positive numbers. And for lower bounds, it only works for negative numbers. Okay, so let's say I want to test 3 as my upper bound limit. Then I will synthetically divide my polynomial by 3. And if all of these are positive or 0, including the remainder, then there are no values greater than 3 with an f of x remainder of 0. So the graph is never going to pass through the x-axis to the right of 3. That's what the upper bound test is. When I synthetically divide by a number, if all of the answers are positive and the number I'm dividing by is positive, then there are no zeros to the right. The lower bound test works very similarly. Maybe I wanted to test -5. If the number that I'm testing is negative, then the results will alternate. Positive, negative, positive, negative, and then the remainder falls in that pattern as well. 0 could count as a positive or a negative. It could also start with a negative. So it just alternates, positive, negative, positive, negative. 0 counts as both positive and negative, so it doesn't break the pattern there, okay? Then that's a lower bound. That means there are not going to be any places where the graph crosses the x-axis to the left of that number. You can't use the lower bound test for positive numbers. You can't use the upper bound test for negative numbers. It doesn't follow the pattern, okay? So for an upper bound, if everything, the number that you're dividing by, as well as each part of your answer is positive, then you don't have to test any bigger numbers. So you don't have to test 5, you don't have to test 7, you don't have to test 36. For the lower bound, if I'm testing a negative number and the answers alternate, so that could be 5, 0, 2, -7, 13, 0, right? 0 can be counted as either positive or negative as long as it counts in that alternating way. Then you don't have to test any numbers below -5 in this example. Okay, we'll do an example for the lower bound test next class, but I just wanted to tell you that there is a way to know and kind of introduce it to you. So your homework is going to be this example. You're going to follow the steps that we did together, okay? Finding the real zeros. So what were those steps? You're going to look at potential rational zeros. That's that list of last over first. looking at all of those factors of 8 and factors of 2, right? Then you're going to look at the graph to know which should I test. And then you're going to test with synthetic division. Practice your synthetic division. So test it with synthetic division, and part of that is write the factored form. And then you're going to find any, if there are any, find if any irrational zeros. And that will give you all the real zeros. The rational and irrational together are all of your real zeros. Okay, so give that a try. We'll go over it together in class on Thursday.